Now it says now, calculate the matrix product AB, where A is 1, 1, 2, 3, and B is 1, 2, 0, 1. So let's work out the matrix product AB. So now the matrix product AB is going to be equal to, let's multiply them. First we go row by column. 1 times 1 is 1, plus 1 times 0 is 0, so this part is just 1. Then we go first row times second column. So 1 times 2 is 2, plus 1 times 1. That's 1, 2 plus 1 is 3. Then we go second row times first column. 2 times 1 is 2. And then we go second row times second column. 2 times 2 is 4, plus 3. 4 plus 3 is 7. So AB is 1, 3, 2, 7. Now it says show that the matrix product is not commutative. So now that we find AB, we just need to find BA. Now the matrix BA, we'd have to put B first, which is 1, 2, 0, 1, and multiply that by A. Of course, A is going to be 1, 1, 2, 3. When you multiply this across, what we're going to get is row by column. 1 times 1 is 1, plus 2 times 2 is 4, 4 plus 1 is 5. And row by column, 1 times 1 is 1, plus 2 times 3 is 6, 6 plus 1 is 7. And row by column, that's 0 plus 2, 1 times 2 is 2. Then we have row by column, 0 times 1 is 0, plus 1 times 2 is 3. Now as we can see, we get 5, 7, 2, 3. All right, and so it's not commutative because AB is not equal to BA. So we've shown that it's not commutative. Of course, they're going to ask us the next boring piece, which is to find the inverse. The inverse of a matrix is equal to 1 over the determinant times the adjoint. So it's equal to 1 over the determinant of the matrix, 1 over the determinant of the matrix A times the adjoint, all right, multiplied by the adjoint of A. So let's work that out. Now, the determinant of A is going to be the product of the leading diagonals minus the non-leading. 1 times 3 is 3. 3 minus 2 is 1. So we're getting 1 times the adjoint of A. Adjoint of A is we interchange right here. So we have the adjoint of A is going to be 3, 1, negative 1, negative 2. So this is the inverse of A. 3, negative 1, negative 2, 1. That's the inverse. Now the next part, part 4 says, given that m is equal to 2x, 2, 9, and 3, calculate the values of x for which the determinant of m is 0. Now when the determinant of m is 0, that means the product of the leading diagonals, which is 6x, minus the product of the non-leading, 9 times 2 is 18, that's equal to 0. Now 6x minus 18 is equal to 0, then clearly x is 3. So clearly x equals 3. Now part B. Part B says that the position vectors of R, S, and T is such that it tells us that OR is negative 3, 4, OS is 1, 1, and OT is 5, negative 2. Calculate the magnitude of vector OR. So the magnitude of vector OR, so this means magnitude for vector, the magnitude is going to be equal to, OR is negative 3 square plus 4 square square rooted, that's 5. When you square root it, you get 5. Nice and easy. It wants us to work out vector RS. Now vector RS is equal to vector of the last minus vector of the first. That's vector RS. Vector of the last minus vector of the first. Vector of the last, OS. This is now 5, negative 2, minus vector OR. And vector OR is negative 3, 4. So 5 minus minus 3, that's going to be, RS is 5 minus minus 3, that's 8. And negative 2 minus 4, that's negative 6. So vector RS is 8, negative 6. Then it wants the vector ST. Vector ST is OT minus OS. It's always vector of the last minus vector of the first. So vector ST is OT minus OS. So vector ST is going to be equal to, OT, by the way, is 5, negative 2. OT is 5, negative 2 minus OS, and OS is 1, 1. My gosh, we made a mistake above here. OS is not 5, negative 2. OS is 1, 1. So this is a little minor error. This should be 1, 1. And 1 minus minus 3 is not going to be 8 minus 6. 1, 1. That's going to be 1 minus minus 3. That's 4. And then 1 minus 4 is minus 3. And then now OT minus OS is this. Now we work it out, we get 5 minus 1 is 4, and minus 2 minus 1 is minus 3. So what can we see right here? We can make a conclusion that RS is equal to ST, don't it? Before we even go no further, clearly RS is equal to ST. And then what does that mean? It has a common point both being S, and so RS and T are collinear. I can guarantee that's what they're going to ask next. It says, using the results, combining, justify that RS is parallel to ST and that RST is a straight line. No, that's what we just said. We just proved that RS is equal to ST. All right? RS is equal to vector ST. All right? That's the first thing. And they have a common point. They have a common point T. They have a common point T. Since they have a common point, so R, S, and T are collinear. Since they are collinear, hence RST forms a straight line. Nice and easy, soft. So if you wanted to verify this, right, what you could do is you could go ahead and plot a graph, and you will see that RST is going to give you a straight line. Right? Let's say you wanted to plot the points, right? I'm going to show you. Let's say we wanted to plot the points. Let's go with a new graph. Let's say you're plotting those points. And the points we had again are -3, 4, 1, 1, and 5, -2. So let's plot these points. -3, 4, 1, 1, and I think the last one was -5, 2. Five, -2. The last point is 5, -2. 5, -2. All right, so let's label the points. There are the points. All right, these are all in a straight line. You could just connect the line now. You could see that all of this is just one straight line. All right. There it is, one straight line going through them. So R, S, and T's indeed form a straight line. They are collinear. Nice and easy. And this concludes this paper. 2015, soft, the capital T. So again, I'd just like to ask that you subscribe to the channel. Please subscribe, help the channel grow. And all the best prepping for your exam. Stay tuned for more.